Hey, welcome. How's it going? It's a new video just for you. So this one is about implicit differentiation. I'm trying not to cough during this, but I feel one coming on, so I'll edit it out though. I promise you as we go. So we're going to talk about the difference between explicit versus implicit. Underneath here we've got some links. So if something's explicit, it's fully and clearly expressed or demonstrated, as it says there. There's a clear relationship from one thing to the next. Whereas if something's implicit, excuse me, the relationship's implied, so it's not expressly stated, so there's some implication. And you've had things where, agreements are implied rather than someone saying, yes, you can clearly do that. But with math, we're talking about explicit being having the dependent variable expressed directly in terms of the independent variables, such as that right there. Okay? When it's implicit, the dependent variable is not explicitly expressed in terms of the independent variables, so like x squared plus y squared is equal to 1 would be sort of an example. So, depending on what x is, y is going to vary. Depending on that, we don't have it clearly solved. They're somewhat related to each other. There is a relationship that's implied, but it's not a straightaway one. Okay, things like y equals 6x squared plus 4, that's explicit, whereas xy equals 4 is implicit. Okay, the thing with this one is I could quickly turn this into y equals 4 over x, and then if I know what x is, I get y, so that I can make that implicit equation into an explicit equation. But, however, if we look at this one, y equals the square root of 3x to the 4th minus 5, how about that? That one's explicit. We know if I put x in, I raise it to the 4th power, multiply by 3, subtract 5, and as long as I don't get a negative number underneath the square root sign, I will get a real answer out. But here I've got x squared plus 3y squared plus 6y equals 8, and I'm not going to have a whole lot of luck solving that for y, so we've got to figure out a way to work with that as we work through this particular topic, which is implicit differentiation. That's the wrong one. It's this one. Silly. All right, so implicit differentiation is what we're going to use to attack something like this thing that was on the previous screen. I don't know where it went. Where'd it go? Can I go back? Oh my God. What's up with that? Like that. Huh. It's odd. Oh, it's Bodkins. Here we go. So, if I want to take the derivative of x to the 5th, why it's 5, x to the 4th. Okay, that's the derivative of x to the 5th with respect to x. If I want to take the derivative of y to the 5th with respect to y, why it's 5, y to the 4th. However, here and so if I want to take the derivative with respect to x of y to the 5th, well, I could write down it's 5 y to the 4th. However, that would be the derivative with respect to y. And I want the derivative with respect to x. So what I do is then I just multiply by the derivative with y of y with respect to x. So I would say that the derivative with respect to x of y to the 5th is 5y to the 4th dy dx. Okay, and that's what that says really there, but I don't have quite the ability to get to the little pointy thing, but you trust me that that says derivative with respect to y times dy dx. Okay, so we'll see how that plays out in a problem like this. Okay, so this is the original problem that we couldn't solve before, and we want to try to find the derivative. And again, when we're finding the derivative, we're trying to find the instantaneous rate of change. We're trying to find out how this thing is changing as time goes by. If we get some sort of a function that behaves this way, we want to know how it's changing as we go. So, derivative of x squared, well, it's still 2x, so that's easy. Minus the derivative of 3y squared, well, right away we might say it's 6y, but with our newfound implicit differentiation, we always have to multiply by dy dx. Okay? And the derivative of 6y is 6, but it's 6 dy dx. And the derivative of 8 is 0. Okay? So these dy dx's I can rewrite as y primed. Because it means the same thing. It's a whole lot easier to make a y prime than it is dy dx. So I could just rewrite this, and this is just for the sake of my laziness, plus 6 y primed is equal to 0. So we want to solve for y primed. So we want to get y primed all by itself. So what we'll do is, well, I'll get rid of the 2x, and I'll just leave this as negative 6y y primed plus 6y primed equals negative 2x. And then I will factor out y primed because both terms have a y primed. I'm left with that. And then finally, I'll go over here because I'm running out of space a little bit. Finally, y primed is equal to negative 2x divided by negative 6y plus 6. And so that is how this is changing. If we want to know specifically at a specific point, we need an x value and a y value at a specific point. We can plug it in and we can figure out the rate of change at that particular moment. Okay? So that's how it works. Let's give you some details. So there's some rules. What we do is we find the derivative. We include, if it's an x term, we just do like we've been doing. If it's a y term, we just take the derivative sort of like we've been doing, but we have to pop a y prime down at the end. Our strategy then might be to gather all our y prime terms on the left and the other ones on the right. And you can do it the other way if you prefer to put things on the right, the y primes on the right and the others on the left. I don't really care. Basically, y prime terms on one side, not y prime terms on the other. Factor y primed out of the ones that you've got all together, and then you do a division, and that gets y primed all by itself, which is the derivative, the slope of the tangent line, the instantaneous rate of change. You've got to follow all the rules. So the product rule, the quotient rule, all those things still are part of our deal as we do this implicit differentiation. Okay? So we look at this one. 3xy plus 6x squared minus 4y equals 11. We want to know how that thing's changing. We want to know the instantaneous rate of change. So we've got to take the derivative of 3xy. 3. Now, xy means x times y, which means we have to use a product. So for the product rule, we do the first, x, times the derivative of the second, plus the second, y, times the derivative of the first. And the derivative of x is 1, so I'm not going to bother to write that. Okay? And then we'll just continue on, plus the derivative of 6x squared is 12x, minus the derivative of 4y, which is 4, y primed, equals the derivative of 11, which is a constant, equals 0. Okay? Here's a little FYI for you. Every time you take the derivative of xy, and you'll do it a bunch of times, every time it's xy primed plus y, regardless. And then I pull the 3 out of the way so I don't have to worry about, well, what happens. It does require another step to multiply it back in, but I just like to try to pull those numbers out so I'm not sure, like I'm not doing 3x times 3y or what have you. All right, so now we just distribute, make it look nice. All right, and then let's see, what do? We get our y prime terms together and our not y prime terms together. So we've got 3xy primed minus 4y primed equals negative 12x minus 3y. Factor y primed out. Divide. There's our answer. Okay. Now, if for some reason we pulled all the y primes to the other side, we'd get the exact same answer, but honestly, what would happen is all the signs would be opposite. So it would be, 12 plus 12x plus 3y divided by negative 3x plus 4. So if you ever get a situation where you look at the answer book and you have the same terms, but all your signs are opposite, it just means you move things to one side and they did to the other, but they're going to be equivalent. Again, this is a function. It's how something changes. And if we want to know what's the rate of change at any particular point, we'd know the x and the y coordinate, plug them in, get ourselves a number, instantaneous rate of change. Okay. So here's something, the kappa curve, which is, we want to find the equation of the tangent line at 1, 1 for the kappa curve. And so it's this crazy thing here. And there's the point. We want to know the equation of that tangent line right there. Okay. So let's take the derivative. First, because it's a product, right? Times the derivative of the second, so the derivative of x squared plus y squared is 2x plus 2y, y primed. So the first times the derivative of the second, plus the second, which is this x squared plus y squared, times the derivative of the first, which is this 2y, y primed. Okay, so we've taken care of this side, equals the derivative of that side, which is 4x. All right, we got to do some little multiplying and stuff to make it all look nice. 2x y squared plus 2y cubed y primed plus 2x squared y primed plus 2y cubed y primed equals 4x. Okay, and make sure that when you're doing the multiplication, you don't write this as y squared 2x or something like that because it just looks crazy. Put your coefficients out in the front, make it all nicey nice as we go. Y prime terms together, not y prime terms together. I get 3 y prime terms, the other one. So on this side, I'm going to have 4x minus 2x y squared. I'm going to do a double move here, and I'm going to factor the y primed out at the same time. So y prime times 2y cubed plus 2x squared y plus 2y cubed. Okay, that's what we get. My derivative then turns out to be y primed equals 4x minus 2xy squared over 2y cubed is 2x squared y plus 2y cubed. Whew, there's a mouthful. Okay, so that's the whole thing. Now we can actually answer the question. Find the equation of the tangent line when x is equal to 1 and y is equal to 1. So we evaluate this at 1, 1. So on the top, well, it's nice, it's 1s because all 1 squared and all is the same. So the top I get 2. On the bottom I've got 2 plus 2 plus 2, which is 6. 2/6, aka 1/3. So now, our friend the point slope equation tells me y minus 1 equals 1/3 x minus 1. Ta-da! Done. Find the equation of the tangent line. Okay, using implicit differentiation. It's long, there's lots of places for little mistakes. Take your time, write them all out. Make sense of it. That's it. Those are the problems you're going to see. The Tootsie Roll Pop data we've done already, I'm pretty sure by this point, so you'll be needing that pretty darn soon. So, that's it. That's all. I think, yeah, I'll go have some lunch now. So, this is a new one. We'll see you soon. Hope you learned something. Thanks for dropping by. Bye-bye.